So Dr. Picker got his PhD at the University of Sydney, and since then has been a postdoc at UCLA. Joined us in September.
All right. Thanks for having me. Although I'm not sure you had much choice. I think this was just imposed upon you. And I can't believe I forgot to put the doctor there. You get 0 opportunities to call yourself doctor, and I wasted one. Because I think the only time it's ever happened is at the airport. So, yep, as Joe said, I'm in the Q Heat group with these guys, and I'm going to tell you about some stuff that I care about, I guess, if this works. Okay. So I'll start with a quick outline. I'm going to start by just introducing myself, some of the stuff I've worked on in the past, some of the stuff I'm thinking about right now, and just tell you stuff that I care about that is not actually in the content of this talk, with the idea that if anybody wants to, they can come and find me. Anupam and I are in the MI Theory office, if you know where that is. We're usually there if you want to have a chat. Actually, we're mostly messing around almost all the time. So, but after introducing myself, I'm going to give a talk that's less about my work and more just propaganda about the things that I care about. So I'm going to talk a lot about primordial black holes, right from the basics, tell you about all the interesting things, and then go into sort of the broader world of macroscopic dark matter, composite dark matter. And specifically the stuff that I've worked on are these last points. So some stuff about how dark matter interacts with asteroids and rings and craters. And if there's time for it, which there might not be, depends perhaps how many questions you guys ask, I'll tell you about some work I've done which is about making balls and black holes at the same time. So it has to go at the end, otherwise it doesn't make any sense. But we might not get there. So I'll start with some introductions. As Joe said, I started at the University of Sydney, did my PhD with Celine, Bohm, and Archel, who are very much kind of classic dark matter particle people. Archel's more on the formal theory side, but he's a fun, crazy person. And then I headed to UCLA, which does, in fact, there is snow present at UCLA sometimes. This is with a telescopic lens, so this snow is actually not that close to UCLA, but in principle, it is visible. And I was working there with Alex and Graciela, who are sort of, I guess, older names in the dark matter particle physics scene. Alex did a lot of stuff on supersymmetry and cue balls and stuff, and Graciela did a lot of the early good particle cosmology work. And now finally, I'm here at sunny Queens. My wardrobe has been well equipped for the weather here in my life up to this point. And I'm working with Aaron and Joe, of course.
For the time being.
Yeah, this is already the coldest I've ever been. Oh, no. Don't tell me that. Actually, I would not mind going to Antarctica. So here's some past work that I'm just not going to talk about today. I've done a lot of different work on primordial black holes, specifically some formal stuff about different metrics other than the Schwarzschild one, and things relating to Hawking evaporation. I've also done some work on axions, multi-axion models, the phenomenology associated to those, and like kind of a more specific look at how they form domain walls and how domain walls collapse and how they produce gravitational waves, these kind of things. It's like a very preliminary plot from this paper, which is not out yet. I've also worked on some supermassive black hole formation, so direct collapse, including dark matter. I think maybe some of you actually do work on this, so I apologize that I'm not going to talk about it at all today. But I'm always here to chat about it. And then miscellaneous astroparticle stuff. So I guess you're not a real astroparticle person if you've never worked on the GeV excess. So you have to have at least one paper on that. And then gravitational waves of all kinds.
The share screen seems to be not working. Could you reshare?
Yes.
Reshare it again.
I may.
Sorry.
Was it frozen or just not doing anything? Okay, just tell me if it stops again. Print, click back. So what am I working on today? What have I been thinking about? So the last month or so, I was trying to see if you could detect dark matter with Saturn's rings. I think the answer is no, unfortunately. The answer is actually kind of marginal, which is the hardest paper to write about. It's there is sort of an effect, which maybe is interesting. With Joe and some other students, hopefully, and some geologists, we're starting to look at a more detailed study of how dark matter could make impacts in craters on planets and moons. With some old collaborators, I'm still working on some beyond the standard model quark nugget ideas. And with Aaron and a host of old friends of Queens, where's Aaron? Aaron's over there. We're thinking about long-range forces in the early universe. And still with some past collaborators at UCLA, still working on axion domain wall collapse and these kind of things. So it's not quite talking about these today, but just stuff that I'm thinking about right now, in case anyone happens to be interested. But let's talk about dark matter. So here are, I guess, the quickest overview of all the possible candidates you can do. I'll spare you all the normal evidence and stuff. You guys all know it. So of course, you could modify gravity. Maybe that's not so easy, but it is potentially possible. And then there's our favorite particle candidates. You have the classic WIMP or thermal relic of some kind. You have axions, QCD axions, and then you could have sterile neutrinos, so that the abundance doesn't always work out so well. And then we have macroscopic things of various kinds. So we have quark nuggets, we have cue balls, which I only learned kind of recently that the cue in cue ball is actually meant to be like a pool cue ball. Like that's the pun they were going for originally. So cue balls and black holes. And those things are the topic of this talk today. So I'm going to go out of order and start with and primordial black holes because it's sort of the simpler of the two. It just works better for the flow. So you'll have to forgive the talk title. But I want to go right back to the basics. Because the point of this talk is not really to tell you anything technical about my research, at least in my opinion. The point is that if you're a grad student in some other group out there and you've never heard of primordial black holes, maybe the only thing you know is that they're less favored compared to particles or something like this. I would like to disavow you of that opinion. And maybe by the end of this talk, you say, maybe. That's fine. That's a success as far as I'm concerned. So basics. Primordial black holes did not form from stellar collapse. They form in the early universe with an asterisk because exactly what that means is not completely fluid. And we distinguish them from supermassive black holes on a sociological level. I'm sure those are black holes which are not stellar, which form in the relatively early universe, but we're just kind of different fields. So they get lumped into a different thing. Although we did have a good journal club about sort of primordial black hole, supermassive black hole formation a couple weeks ago. So it's probably somewhat familiar to you. And of course, they're an extremely simple cold dark matter candidate. They're like the perfect cold dark matter candidate. In fact, they just zoom around not doing anything. We have not seen one yet. Maybe we will. So some basics. How big is a black hole? Here I've put the kind of mass scale that you might expect a PBH could live in, anywhere from the Planck mass, which is about the weight of a fly, to a galaxy-sized thing, which probably would not be a good dark matter candidate, but in principle, you could have such a large black hole. And here's what the radius of those objects would be. So for a kind of mountain mass, it's about the size of a proton, which is very, very small. The Earth mass is about the size of one finger. And sort of my favorite one is that a solar mass black hole, if you've ever been to Fermi Lab and you've gone up Wilson Hall and you've looked at the Tevatron ring, it's pretty much the exact size as a solar mass black hole. So you can picture in your head, if you've been there, what that would look like to see. Something interesting to note from this is that black holes become less dense as their mass increases. Maybe this is like kind of a trivial point, but the radius goes proportional to the mass. And normally in matter, the mass goes like the radius cubed is some density, right? And so the bigger they get, the less dense they are. And in fact, Joe doesn't like this, but it's very easy to show that the Schwarzschild radius of our universe, of our Hubble patch, is the Hubble horizon. They're exactly the same. You can take your Friedmann equation, divide it by just the mass of all the stuff in our universe, and then you get the size is this. So Joe will claim something like, oh, it has to be the right flatness or something for this to work, but
There's actually a slightly different measure for this as well.
I just think it's a fun fact that makes you sound like a crackpot if you say it, but it is true. And that's the goal in life, is to sound like a crackpot but be correct. So, primordial black holes, don't they evaporate? How can they be dark matter if they evaporate? It's true that Hawking radiation is produced by black holes, and so they lose particles. The mass of a black hole, which evaporates with the lifetime of the age of the universe, is 7 times 10 to the 14 grams, which is about a very small asteroid or mountain-ish size. Everything above here has such long lifetimes, these are years here, that they're effectively cosmologically stable. And I'll just plug some of my work there. You don't have to look at it. But how abundant would they be? So in units that are more favorable to black holes, the local density of dark matter is 0.01 solar masses per parsec cubed. So that means if you have an asteroid mass black hole, there's about 1 in our solar system at any given time. And that means they're traveling through for like a couple of weeks or so at the speed that dark matter moves in. If they were Planck mass, there'd be about 1 per black sea of volume. And if they were solar mass, there would be 1 in our kind of local collection of stars. If that seems weird because you know there's more dark matter than regular matter, that's just because the halo is much bigger than the disk. So that's why there's less than that. And of course, per galaxy, there's 1 per galaxy. Not very interesting. Another frequently asked question, do they smash into things, or would they smash into things? What would happen if they smash into things? As we've seen from the previous slides, even if they're small, this happens very rarely. So the consequences are not so massive, but in principle, this is what happens. For a sun or a star or something, they just pass right through. You would almost not notice a single thing. For terrestrial bodies, they've kind of simulated, and you expect about a 1-meter crater on either side if it's an asteroid mass primordial black hole. For white dwarfs, it was thought that maybe they would ignite some kind of like flash around the outside as they pass through, but now it appears that they do not do that, actually. But for neutron stars, and I'll come back to this later, it is possible for them to capture a PBH and then slowly suck it into the middle, just because they're so much more dense than other objects.
Crater burnout. I mean, shouldn't the crater size depend on the dark matter particle size, like an actual asteroid, or is it a different type of interaction than a regular? It's
a different type of interaction because the Schwarzschild radius of an asteroid mass black hole is about a proton. Yes, sorry. Usually the mass is the kind of descriptor, yeah. Yes, that would be very large, yes. And the likelihood of that hitting the Earth is extraordinarily low, so I would not worry about it.
Oh.
You worried about it? Oh, you'd like to worry about it. So you might be saying to yourself, how are we possibly going to see something that doesn't almost do anything? And the answer is, okay, yeah, you're probably right. It's very, very hard to come up with ways to find primordial black holes. This is just one recent paper, which I think is interesting. It came out from some friends, where they were showing that we have like almost 30 or 40 years of very precise distance measurements to other planets, so Mars and the Moon and things like this, like to centimeter precision for Mars, I believe. And so if a primordial black hole passes through the solar system, it'll very subtly change the orbit of the planets, and you would be able to track that over a perturbation which grows over the 30-year span. Is this actually feasible or not? I don't know, but it's a possible way that we could be thinking about finding a primordial black hole. All right, another question. Would they be smooth enough to be the cold dark matter? I mean, I just said that there's one of them per patch of local stars or something like that. Does that actually work? And the answer is, well, what is the smallest length scales that we actually measure dark matter on, like in terms of like how we observe dark matter? And as far as I can tell, at least locally, the best you can get is probably from parallax measurements of nearby stars, say Gaia. Here's a plot from that where they've taken some measurements that are a bit closer than like a kiloparsec or so. So it's not really going to affect the smoothness on any scale that Gaia could see, at least for most of the primordial black holes we care about. You might have better luck looking at like microcaustics from lenses, because those can probe very small scales as something passes in front of it. You could measure the smoothness of dark matter. The limits are really not quite there yet to say anything very definitive about PBHs, but maybe we'll get there soon. They're definitely going in the right direction. So I've been hinting about it. How do you detect or constrain primordial black holes?
Go back one minute. I think that might be the first time I've ever seen the word microcaustic.
Don't ask me about this. So, okay, I know what a caustic is, but I don't know what the difference between a microcaustic and a caustic is. Caustic is like, you know when you look in the pool and there's like bands of white light? That's like a caustic where the lensing has conspired to make like an extra bright patch in some way. And so you can see this in the way that gravity works also if you look at clusters. So there'll be lines where there's like kind of extra stuff, extra luminosity. I don't know how you measure these things, but they look like these kind of funny bounds. And you can tell the smoothness by looking at how wiggly these bounds are, essentially. All right, so what does the constraint plot of primordial black holes look like? You've probably seen this before. But if you saw it more than maybe 10 years ago, it looked quite different. And that's because a lot of constraints have been disappearing faster than we're making new constraints. As it turns out, actually, a lot of these are more subtle than initially presented, and I'll talk about that as we go. So on the x-axis, we have the mass in solar masses, and also in grams, if you care. And the y-axis, this is a lovely thing you can only do for PBHs. This is the fraction of dark matter that is in PBHs. So for a usual dark matter plot, you can't show this because you need to have the cross-section on the y-axis. But now we get this extra dimension, which can show the space much more cleanly. So on the far left end, this is where they would evaporate, and you would see them in cosmic rays or gamma rays or something like this. Here we have microlensing surveys, which cut out sort of moon to planet sized, maybe solar mass sized primordial black holes. Then at the high end, we have gravitational wave production. You have accretion onto the black holes, and then we have dynamical constraints. And I'm going to talk about all of these in a second in more detail. But obviously, the most interesting feature is this one, the asteroid mass range, which is completely unconstrained from anything up to this point today, and so makes a perfectly good dark matter candidate. But the other thing which I always like to point out is this line here. If you're on this side of the line, there are more PBHs than stars in our galaxy. So even if you find yourself down here and you're sulking like, oh man, it's not the dark matter, that's actually still a lot of primordial black holes. And so they're an interesting object to study, irregardless of whether or not they are all of the dark matter. We would learn a lot about our early universe from a discovery of a primordial black hole. That's just a fun little thing. So let's start at the heaviest end, at the dynamical constraints. So these constraints are when a big black hole disrupts some kind of astrophysical system. Say, for example, a very wide binary. We know they're some number of years old, and so at some point, a PBH would go through them and disrupt the wide binary. So you could constrain this kind of mass space here. You can play similar games of various kinds with dwarf galaxies, globular clusters, blah, blah, blah. The incredulity limit is there's 1 per Hubble patch. So if you're down here, there's less than 1 per Hubble patch. And you can also constrain it based on structure formation. So you don't want to have too early structure formation, which happens if you have large Poisson statistics from having very heavy black holes. So that kind of constrains this part of the parameter space. I think these are very robust constraints in general. Of course, there's always astrophysical uncertainties and various kinds, but the physics is pretty well understood. So I'm not really concerned about these.
So in this limit where you have a single large primordial black hole that makes up, say, a dark matter halo.
Yeah, that wouldn't work, but yeah. Yeah. So this region does not actually give you dark matter. Yeah.
Okay. It'd be a little more to the left.
There's some limit which says like it actually is dark matter, and that comes in below the size of galaxies. Yeah.
Yeah, I had the same question about that parameter space. Couldn't you just make a bound that says like, in that parameter space, it can't be more than X%, just given CMB constraints on the dark matter?
I 100% agree with you, and it's funny because anytime at UCLA someone would show a plot like this about PBHs, Alex Kusenko would put up his hand and say, "You cannot have dark matter live in this limit," and the person would say, "I just copied this graph from Carr's paper. Like, stop telling me, you know."
Black primordial from it actually was a black hole made by a star.
I think nominally it'd be very hard to tell. You could look at things like spin distribution, but in order to be dark matter, you would need many more of them than come from stars. So
Formed historically in a galaxy, and
yeah, so I can give you an example of an observable. So for absolutely. So for globular clusters.
And the variance, Big Bang nucleosynthesis.
merging and like gravitational waves, like we don't have a good handle on just how
Right, but the dark matter, there's a limit as to how much of the dark matter could have been baryons, not in primordial black holes during Big Bang nucleosynthesis.
Okay, it's not just from us not understanding.
Yeah, I think.
I'll give you an example of the kind of observable you might be looking for. So say for globular clusters, if the dark matter in them was composed of solely 10 to the 8 mass black holes, then it would change the shape of a globular cluster because you have mass segregation. And so
Not of other cluster mass.
these are very heavy. These are 10 to the 7 solar masses, like really heavy black holes. Asteroid mass is down here, where these fake limits don't exist.
That's a primordial black holes, correct? That's what the x-axis is.
Yes, that's right. Yeah.
Yes. I guess a question that I have is how do you place constraints when you don't have good constraints from observations for the stellar direction of the black hole being formed?
So I'm not 100% sure I understand your confusion, but let me just give an example. So if globular clusters had a huge dark matter component consisting of 10 to the 7 solar mass black holes, and they'd had that for the last 14 billion years, then you would have mass segregation taking place on that timescale, and it would change the location of where stars are. Yeah.
An primordial mass black hole that is not at all related to a globular cluster.
Yeah, so I think maybe some of these bounds are the globular clusters getting highly disrupted.
Yeah, that's one way you could place a bound.
There's
Yeah.
There's not a 10�7 black hole
In a
In a
globular
globular cluster.
That's what
There's globular clusters are living, and these 10�7 occasionally pass through them. Are they?
It's a black hole that's being
But they're-
constrained
if they
based on
pass
globular
through-
cluster.
They're if one of these passed through a globular cluster, it would disrupt the cluster.
That's this way, actually.
Okay, okay,
Like it would disrupt anything over 10�6 disrupts
Okay.
the disk.
understood.
Conversely, you can go
Okay, now I think I get
Okay.
it, thank you.
Perfect. No, I love the discussion.
Guys on the left are the penalty dogs?
These guys?
This is a separate plot.
Oh, I don't know. Just the way they made the paper. These are from structure formation, so it's a different observable. Yeah. But they're both essentially dynamical things. All right, great. So at a slightly lower mass range, you can place limits from accretion onto these black holes. So if they're just floating around the galaxy, interstellar media should accrete onto it, and that will produce optical and X-ray observations. And that would also be visible in the early universe, where you would see it in Planck and other CMB, like anisotropy observations, because these produce a lot of radiation. There's a cutoff here because say you have a large black hole in the early universe, and I have another particle nearby which I want to accrete onto it. If that wants to be accelerated towards the black hole, it needs to feel a stronger force than the Hubble pull, which is dragging it away from the black hole. So in other words, there's a kind of decoupling distance where the accretion disk can form. And for bigger black holes, that doesn't happen until too late. So you would just not see it in the CMB. So you actually wouldn't expect to form an accretion disk before the CMB. These constraints are less good than the previous ones, I would say. As a general rule, these can move an order of magnitude in either direction. It's very hard to do the accretion physics, especially for like one solar mass black holes, because we just don't know a lot about how it would work. But I brought up the decoupling there because you can ask a very similar question with two primordial black holes in the early universe. There's some limit where they will decouple from the Hubble flow and form a binary themselves. And actually, you can show that this is a really probable process. You expect almost every primordial black hole to form a binary in the early universe. It gets some kind of tidal force from the next nearest black hole, essentially, so it doesn't just collapse right into each other. This would then produce a spectrum of gravitational waves, both in the stochastic background and in like events that are happening within LIGO's range today. And so that allows you to place these slightly outdated but still fine constraints from, say, LIGO non-observation of this very large rate, actually. You would expect about 60,000 a year or something from LIGO.
Guys, that's pretty merging, or they just,
So for the stochastic limits, which I think is these ones, they're just a whole background of things which are spinning. But for these ones, they're actually merging within LIGO's like detector availability. Yeah. Yeah, I think so. Yeah, I can't quite remember actually where I got this plot from, but you can do both. Yeah. So moving to smaller masses again, we have microlensing surveys. This is when a black hole passes about halfway between us and a distant source. The light goes around the black hole in both ways, and you get an increase of brightness with a very characteristic curve. So what you do is you put this experiment up in space or wherever, and you just watch a whole collection of stars for as much time as you can and count how many of these curves that you see. So they look at, say, the galactic center, or they look at Andromeda, or the LMC or something, and they place constraints that live in this region here, essentially, moon to planet size. These constraints are maybe the most controversial. They move a lot. So for example, HSC's original constraint shrunk up to there relatively quickly afterwards because they had done some interesting things wrong in their analysis. I have more bones to pick with many of these, but we'll come back to that later. So these are okay constraints. So,
You said that they just look at a bunch of stars and wait to see if they see that characteristic curve, right?
Mhm.
Have they ever seen that?
I'll come back to that. So on the small end, you have Hawking evaporation, which I already alluded to. The black holes are expected to have a temperature which is proportional to 1 on their mass, so they're hotter when they're smaller. I produced a little plot here where you have the black hole mass and the temperature that you expect it to be, and so therefore what particles are available to be produced. So you're always producing massless particles, and it's easy to produce neutrinos also. And then as you get hotter and hotter, you produce more and more things, and so you get complicated jets out of them. It's actually a very interesting and difficult particle physics problem, which I don't really study, but it has kept people occupied for many years now. And the constraints you place on that look like this. So I've actually now, this line here is the mass where it decays at the age of the universe. So everything back here is not good dark matter because you expect it to have decayed by now. But we should look at it anyway. This fraction here is now not the fraction, but it's proportional to the fraction at formation, so not the fraction as measured today. So these ones here are all from various kind of cosmic ray searches, gamma rays, protons, this kind of stuff, electrons. And then you also want to make sure you don't screw up the CMB, you don't want to screw up the BBN, all kinds of things, place constraints on the number of primordial black holes that can be produced. But that's the landscape of constraints. I also like to talk a little bit about some hints and caveats and fun things about PBHs. If you are interested in this, easily the biggest kind of cheerleadery paper is this recent one called A Positivist Perspective, where they go through everything that could possibly be construed as a hint in the direction of primordial black hole dark matter. Some of them are believable, some of them are fanciful, but it is an enjoyable read. So if you're interested, I recommend it. But I'm not really going to talk about anything they have to say. So you might be hopeful if you care about PBHs. Maybe we'll see them in LIGO soon. Maybe we'll see a subsolar mass merger, well, any day now. In fact, not that long ago, like a couple of weeks ago, maybe, there was this event, which looks to be subsolar mass. Does not really have a great false alarm rate. I think you'd like that to be much longer than the runtime of your detector, I would guess. I'm not an experimentalist. But this is the kind of thing that we're hopeful to see. And of course, LIGO's observed spectrum of black holes has been interesting and very much non-trivial. For example, there's this excess at 35 solar masses, which is not completely trivial to explain with standard stellar properties, as far as I understand. So people are still writing papers trying to get it there, but I don't think we've converged on an origin for it. And the second thing is there's probably this thing called the pair instability gap, which is where you expect the core of a star to get hot enough that you form electron-positron pairs, and that essentially sucks all the energy out of the star, and you shed mass and get into these cycles of various kinds. But in principle, it should stop the formation of black holes larger than about 50 solar masses. There's some argument about exactly where this bound is, but we have seen black holes in this mass gap, and we're seeing more of them. Could this form from some hierarchical merging scheme? Probably, possibly. I think it's not also completely trivial to explain them, but it's interesting to see what happens here at the very least. But I told you I'd get back to the microlensing events. So in fact, the microlensing surveys have seen quite a large number of microlensing events. Ogle in its 2 runs saw 6 in its first and 17 in its second. HSC in its 1 run officially saw 1. As I understand, they're reprocessing their signal for the last 2 years with a better template matching algorithm, and that number is not 1, but it has not been published yet, so I'm not going to tell you what the number is. The thing which is kind of frustrating is that, at least for Ogle, the way they place their constraints on that map is they say, assuming none of those were PBHs, here's what the constraints would be. Now, of course, there is a background. You expect a background of rogue planets, probably in the order of magnitude of those numbers, but we don't know how many rogue planets there are, and we don't know if any of those were rogue planets or PBHs. So really what you should do is marginalize over what's the chance that n of those 17 were PBHs, and then go through that. And that almost completely destroys their constraint, but they don't like being told that. Here's the kind of plot that already exists, which sort of shows you the combined region where you might expect primordial black holes to live with just these 6 and 1 kind of events. And so you expect actually not an insignificant fraction in the kind of planet to mass range if you were really gung-ho about these being primordial black holes, which I'm not saying I am, but in case you were.
That's the number of microlensing events.
That's right. So Ogle looks towards the galactic center. Sorry, it's down here, but sort of moon to planetary mass. Yeah. They're both a little bit sensitive to different ranges because the distances they look at. Ogle is looking at the galactic center, so you expect a large background of other things. But HSC is looking at Andromeda, so you expect very little background of other things comparatively. Oh yeah, there's also some evidence that maybe you can see them in quasar microlensing things where you have multiple images of quasars through some galaxy cluster. The claim for Michael Hawkins is that the variability of these is not able to be explained by the standard quasar timescales of variability. I don't know anything about that. He's an interesting person, so maybe.
You mentioned the planet
Yeah,
background.
sure.
Is there any constraint on that?
We were talking about that at lunch, actually. I think it's very hard to predict what the expected number of rogue planets are. 1 per solar system, 10 per solar system? I don't know. It should be a lot. Like, I wouldn't be surprised if those were all rogue planets, but we don't know. Like, there's of course more subtleties. So, firstly, primordial black holes cluster on small scales very differently to cold dark matter. So where you would expect a very smooth small scale distribution, for primordial black holes, you expect these kind of Poisson statistic-y sort of fluctuations. And these drastically change the way that the limits work and are not always computed very carefully, especially for many of the constraints. Secondly, I didn't talk about it, but all the constraints I've looked at so far were, are the primordial black holes all exactly this mass? Call this a monochromatic mass distribution. In principle, that's probably not actually correct. They're probably at least something more like a log normal or a much wider distribution. And the wider you get the distribution, the harder it is to set constraints, essentially. Here's the kind of central mass of your log normal distribution, and there's the width in decades. And so the more decades you cover, the kind of hazier the constraint space becomes. Another fun kind of, this is just an interesting tidbit, is that when we first saw the famous neutron star collision and we followed up with EM, and then there was a million newspaper articles that say like all the gold in the world is produced at the neutron star collisions. We've seen it, right? And the rate that you predict is exactly what you need to get all the R process nucleosynthesis that needs to be explained. Unfortunately, we haven't seen one since then. And every day that goes by that we don't see one, we have less and less of the R process nucleosynthesis happening from a location that we understand. So it's gotten to the point, as far as I understand, that we now no longer know where the R process nucleosynthesis is happening that's required to explain the abundance of elements. So could black holes collide with a neutron star and destroy it and create R process nucleosynthesis at the site of the destruction? They kind of fling neutron star material into the air. I think Joe's played this game before with other dark matter things. And the answer is it looks like, yeah. So in this kind of region here, the asteroid mass region, if you're above there, you have the right rate of neutron star destruction, mainly in the galactic center, where you can do R process nucleosynthesis. And maybe also explain this like kind of missing pulsar problem from the galactic center. Like, why don't we see any? That's because PBHs keep destroying them too quickly. And this would
So.
of LIGA. Yeah.
The exception of something really lucky happening during an engineering phase, the next couple of months, there will be no more gravitational waves.
That's true. You're right that my claim that the limit's going down is wrong. Yeah.
So yes.
I'm excited for it. I'm excited for it. The other thing that's kind of just a fun extra little bit from this is that we've detected these objects called G objects, which are orbiting Sagittarius A star, the supermassive black hole, very closely. They look like balls of gas, but they're not tidally disrupted as they go by Sagittarius A star. So it's kind of this mystery that people don't know how to explain. And some of my collaborators suggested that these could be the remnants of this destruction, where you now have about a solar mass black hole kind of binding this extra material from the neutron star destruction into these balls, which we've been detecting and are otherwise unexplained. So, kind of fun stuff. But actually, maybe you've been sitting here this whole time like, oh, okay, this is fun phenomenology, but like the WIMP miracle is amazing, right? Axion misalignment, wonderful. Sterile neutrinos oscillate the wrong way, but whatever. How do you make a PBH? Like, why should I care that these things exist? The standard way to make a primordial black hole, this is the maybe canonical way, is you have some overdensity in the early universe, which is seeded by something in inflation. We talked a couple weeks ago at that Not Quite PBH Journal Club about the density contrast you need to form a black hole. It's much larger than what you expect naively from just inflation with no extra features. And you can actually see here what you need. So here's the power spectrum, the numbers. To be all the dark matter, you want your primordial black holes to live on this line here. So this is kind of the scale of perturbations that you need in order to form primordial black holes. So the way to get something up there is to modify your inflation potential with some feature in it, some feature that gives you something at that exact scale. This is it's an easy game to play, and it's been known for many years. The problem with this is that if you subtly change the location or the height of this feature, you massively change this line. It requires extreme fine tuning to get this to work. This is an ongoing debate which seems to rage at many primordial black hole conferences. There's this paper which says you can't do it. Other people, this paper's then rejected. It's blah, blah, blah. It's a whole thing. It's something which is possible to fix with more complicated inflation models or two-field inflation, things like that. But there's more ways to make primordial black holes than this. All you need to do is come up with some mechanism to put a bunch of stuff smaller than its Schwarzschild radius in the early universe. So I'll talk about some other ways to do that right now. One way to do that is from topological defects. So if you have maybe your symmetry of some theory breaks to different vacua, you can form topological features, strings and domain walls, even like these kind of oscillating solutions. If these at some point have more energy density than the Schwarzschild radius around them, then they'll form a black hole. This is actually pretty easy to do, say, if you have a closed string which starts shrinking, or you have a closed domain wall which starts shrinking, which they generally do because the false vacuum expands or decays. So here's a kind of a fun plot of features, but yep, you can make primordial black holes that way. Another way you can do it is with kind of scalar fields. So the old school example is to look at SUSY supersymmetry, where you have a bunch of different flat directions, which you can think of as scalar fields, which just permeate the universe. At some point, these fragment into like little kind of patches, which I'll talk a little bit more about later if we get there. And then those things can merge and easily have large enough energy density to become a primordial black hole and get you really where you want to be with minimal SUSY parameters in the asteroid mass range. Maybe we don't care about SUSY that much, but this is a generic thing about scalar fields. You can also form them from phase transitions and bubbles. So if you have, say, a first order phase transition and you have bubble walls which are colliding with each other, the collisions of those can easily have enough energy density to form a primordial black hole. That's a very early idea by Hawking and Moss. And you can play the game in more complicated dark sectors where you sort of push material into a small enough space where it has to form a primordial black hole. This one I always like to put on because I think it's just a fun idea. So this is an inflationary theory where I have two inflaton fields, but they're just scalar fields. And the potential that they form is kind of Mexican hat potential. And this potential is slightly tilted. And so the way that slow roll inflation works is you start at the top and you slowly roll down around the ring until you get to the bottom, and then inflation ends. But as you do this, there's always some chance that you'll tunnel into the central bit. And so as it's going, you always have little patches of the universe as tunneling. When they do that, they form what they technically, for some reason, call a baby universe, which starts growing in your inflationary patch. Now, the fun thing about a cosmological horizon is that from the other side, it looks like a black hole horizon. You can study the geodesics and convince yourself of this. So these little patches from outside just look like black holes to us. And because this can happen at any point during inflation, you go into there, you end up with a really wide mass spectrum of primordial black holes because this keeps happening throughout inflation. So you can end up with this massive, long, many, many decades long distribution of primordial black holes, which would be very interesting phenomenologically. All right. That's the whirlwind of primordial black hole stuff. We could go a lot longer, but we got to get through things. So let's look at macroscopic dark matter a little more carefully. So the basics of this is that we're talking about dark matter with cross sections and masses approaching regular stuff. So PBHs certainly fall into that for some of the parameter space, but we can go more broad here, and I'll show you what the parameter space of this looks like. So here's mass on the x-axis. Here's your favorite dark matter nucleon cross-section on the y-axis. So up here, we're getting into like, these are like regular object size things. These are geometric cross-sections. And you know, kilograms, gigagrams, blah, blah, blah. Just to be clear, here's where things live on this plot. You can see the black holes, they get less dense as they get bigger. Then you have pyramids, whales, humans, flies, tardigrades, et cetera. They kind of live in this parameter space of roughly water density, essentially. And I'm going to talk about all of these various constraints in the most busy slide of all time. So up here, the constraints we get are from this dark matter igniting kind of thermonuclear flashes on white dwarfs and neutron stars when they collide into them. In this range, we actually have like a big detector network across the desert in Australia, which is just watching the sky and waiting for things to flash. As the dark matter would fall in, you would expect it to kind of do a little poof in the atmosphere. You get constraints here. This crowd favorite one called human death is where you would expect the dark matter to leave unexplained bullet-like wounds in someone's body, which according to them, we've never detected, but they actually did not survey the medical literature to check. It was all wrong, all wrong. In this region here, which is familiar to many people here, you are looking for tracks in either rocks or pieces of plastic as the dark matter goes through and leaves kind of trails. And then we get to the more and more sort of conventional dark matter region where you have like a bunch of liquid scintillator, you wait for it to get something to go through. You can use the calorimeter of like an X-ray telescope that's just sitting up there and use that as a detector for macroscopic dark matter. And then your whole bundle of regular dark matter detection experiments down here. So this is the like kind of crazy parameter space. But you might notice that there are big gaps in this parameter space which have no constraints in them for some reason. Why have we forgotten to look at these? There's this huge gap here and a little gap there. And this is a regime where things are like this size. So like a car or an atlas or a small building or something like that. Nominally, I mean, we should probably be able to detect dark matter that is regular stuff size, right? That's the easiest size to detect. So this is what I wanted to look at. We're finally looking at some work that I've actually done. And this is looking at dark matter interactions in our solar system. So how can we probe into this parameter space a little bit? So why the solar system? Firstly, there's a plethora of well-studied objects. There's asteroids, planets, surfaces, cratering, rings, all kinds of things of all different object sizes, different densities, rocks and ices and stuff. But most importantly, a lot of these have just been chilling there for like 1 billion years. How many like ton years does our best dark matter experiment have? I don't actually know the answer, but probably not billions of years of just sitting around. And so this makes them actually a very interesting dark matter detector. But if I'm being completely honest, mostly it was fun to do this. And so that was the reason why I did it. The scientific impact, whatever. So the first thing we can ask is, does dark matter destroy asteroids catastrophically? So this is kind of a trivial constraint in the sense that there are definitely asteroids today. They have not all been blown up by dark matter. So we can make a very crude estimate in this way. In order to know this, you have to know the average age of an asteroid. This is not a completely trivial question because asteroids collide with each other and have catastrophic destructions with some frequency. Generally, those collisions happen more frequently for smaller asteroids because they're easier to destroy. And you can look at this with simulations or even observations. Here's a plot of Kuiper belt objects of different sizes and the abundance of them. And so there's this characteristic break that occurs where the mass of that asteroid has its like kind of catastrophic destruction lifetime being sort of the age that it is right now. So once you're destroyed, you spread material of different sizes and it changes the shape of this distribution. What this means is you can look at where this little bump is and tell the age of the system. So you can look at the Kuiper belt and say, oh, the Kuiper belt's 4.5 gigayears old because this bump is at this location, which is pretty cool. The way that I estimated this is very crude, but essentially you say, let's let the dark matter plow a hole through a spherical asteroid, figure out how much energy is put into the asteroid versus ejected out of a hole on the other side, and then say that energy would go into shocks, which transfer through the rock and then contribute to its explosivity or whatever, its destruction. The problem is that asteroids are very complicated objects, actually. We expect now that most asteroids are rubble piles. They're not just one solid rock. They're actually a collection of boulders of different sizes pushing against each other. And we see that in all kinds of places. The first one was probably the famous Schumacher-Levy 9 comet, which broke up over Jupiter. We visited a number of asteroids and even plowed spaceships into them. There's the DART mission. And then you can look at the distribution of asteroids in general and see that as they get bigger, there's this barrier that appears here where they just can't spin too much because they're getting pulled apart. They're not actually that closely bound together. So most are probably rubble piles. The problem with the rubble pile is that the more rubbly you get, the harder it is to destroy. So here's a simulation people have done where they plow something into an asteroid and see how hard it is to destroy. This is something that people have cared about for a long time, partly for like defense-related reasons. Like I actually went back through some Department of Defense manuscripts from the 70s and 80s. But also because it's important to understand the formation of the solar system. These processes are important. And luckily for me, this work has already all been done. They have determined how much energy you need to destroy an asteroid of a particular kind at a particular size using a combination of simulations and material, like real material tests and blah, blah, blah. And it looks like this, where you have this material regime where you're trying to overcome the actual, like you're trying to break apart a rock. And then you end up in the much more difficult to disrupt gravity regime, where the dominant force that makes it hard to destroy them is actually like pulling the parts together and having them not fall back into each other. The other thing we can look at, I'll show the results later, is that, okay, say you plow into an asteroid, but you don't destroy it, or you just transfer a bunch of momentum into it. As it turns out, escape velocity is not that much larger than orbital velocity. So if you have a few collisions which kind of transfer momentum to your asteroid, then you could have it just evaporate out of the solar system. And we do not want all of the asteroids to evaporate out of the solar system. So the best way to look at this is Kuiper belt objects, because they have the lowest orbital velocity, so it's easiest to push them out of the solar system. And then you can play the same game with planetary rings. I mean, these are just chunks of ice. And in the outer region, we also don't want to evaporate them too. So we know, I've been looking at Saturn for a while now, we know a lot about Saturn's rings. It's very complicated, but this is a very trivial kind of silly bound that we just don't want them completely destroyed. Finally, you might ask, okay, so you're destroying all these asteroids. Surely we would see this on Earth if there was this many craters. And the answer is, yeah, actually, there should be some overlap with the asteroid destruction constraints and the cratering on Earth constraints. The problem with Earth is that it's much harder to know the geologic history because we have so much active stuff going on. How do I know how many craters happened and then were erased by some kind of tectonic processes or in the ocean or something? It's very hard to have an empirical number there. You can ask, what is the expected number of craters that we would have thought there are based on the known bodies that aren't dark matter? And we can say, well, we probably don't want the number of dark matter collisions to be larger than that, but it's not really a constraint. It's just kind of an estimate. I always like to put this picture up here just because it's cool. The Chicxulub impact event was the one that killed the dinosaurs in the Yucatan. And today, you can still see this ring of cenotes, which are like water holes, which exactly go around like the crater edge, which I think is freaky that you can still see this thing from 100 million years ago. Very cool. But all right, let's look at the results. Here are the constraints that you can place from the destruction of these solar system objects. So definitely the biggest chunk of unconstrained stuff is from the asteroid destruction space. You also don't want to destroy ring particles. You don't want to evaporate the outer A ring. You don't want to evaporate the outer Kuiper belt. And then if there were more craters from dark matter than regular objects, you would have this region here, but it's not really a constraint, at least yet. We're trying to think about a way to make this a real constraint in the future. Yes, that's a good question, which we are trying to do. It's hard because, so dating moon craters or Mercury craters is not really as easy as dating, say, an Earth crater. And we also don't know from like the late heavy bombardment exactly what is the expected number of craters. You could probably place some trivial things, as Joe explained the other day, like there shouldn't be way more craters than we observe on the moon. So probably there's something to be said here in the near future. Yeah. Yeah.
You have a different problem. It's still a problem.
Yes. Yes. So this is the final constraints. I also put on here the density of ice, just so you get an idea, and the density of nuclear matter, because this is essentially where you expect things like quark nuggets and these other macroscopic candidates to be formed. So in the very last moment, I'm just going to talk about some macroscopic dark matter candidates, and then I'll probably end there. Because maybe like the PBH thing you're saying to yourself, like, so what? What the hell are these objects that what's a fridge-sized dark matter? How do you come up with something like that? Doesn't make any sense. So I'll explain some basic things which are, I think, kind of viable. The canonical macroscopic dark matter are quark nuggets. These are like the best idea ever. They're from Witten in the 80s. These should have been the dark matter, but unfortunately the universe has conspired against us to make them not the dark matter. The idea is that if you had a first order QCD phase transition, you nucleate patches of your new vacuum, and bubble walls form. Now, if you have free quarks in the old vacuum and hadrons in the new one, if your free quark is not energetic enough, it can't cross the barrier into the new phase because it just doesn't have enough mass to form like a pion or something on the other side. So you get reflected off this boundary, and as this new phase grows, you push the old phase into a smaller and smaller area, and you compact standard model quarks into a big lump called a quark nugget. Now, This is kind of a brilliant idea because you can actually show that just an even collection of up, down, and strange quarks, just even numbers of all of them, is the ground state of QCD. You might think it's the iron nucleus, and that is a very stable state of QCD, but actually you have lower energy density or higher binding energy, whatever, in this kind of quark matter configuration. And the reason that an iron nucleus doesn't decay into this matter immediately is that you would need like 60 weak transitions to happen at the exact same moment to make this work. And the probability of that is just very, very low. So if you could form this strange matter, then it's actually like an extremely stable state. Now, the reality of quark nuggets. Unfortunately, it seems from lattice QCD simulations that we do not have a first order QCD phase transition. It actually is a crossover transition. That can probably be modified in various ways. But the other problem is that quark nuggets get evaporated essentially by the energetic neutrino background in the early universe. So they plunge into the nugget and just knock quarks out. And you can show, or they showed in the 90s, that the sort of smallest size which could survive this evaporating process is about 10 to the 40-ish number of quarks, which gives you about a moon-massed quark nugget. And that's probably too big to assemble by this process. It just doesn't really work. But it's not completely dead. People are still doing recent work on it. You can do fun things like change the order of phase transitions, and that makes the QCD phase transition first order. This is something that Yang Bai and others have worked on. Then you can even end up with 6-flavor quark nugget dark matter instead of 3-flavor. And then, of course, our fellow Canadian, Ariel Janitsky, and other people have been working on this axion quark nugget idea for some time, where you have a regular quark nugget, but it's like held together by axion domain walls in some complicated configuration. But still, maybe some possibilities. I don't know. Or we could generalize from this very standard model process into a generic dark sector BSM kind of idea. So, I mean, what is a nugget really? It's what we call a non-topological soliton. So it's a field configuration that is stabilized not by its topological configuration, like those strings and things like that, but stabilized by some symmetry of your system. So in the case of the quark nugget, it's baryon number conservation, which keeps them stable. You can play the same game in a dark sector by saying, I have some particle, they get put together into a field configuration, and that's stabilized by a U1, global U1 symmetry of some kind, and that prevents them from decaying. And we call these balls, I guess. They changed the name. There's all different kinds of balls that you can have. I think probably the first one were Q balls. This is when you take a scalar field configuration, and some U1 symmetry keeps it stable. This is fun work from a while ago. I always put this in because I love this line from Coleman's original paper, where he says, unfortunately, I have no idea how to estimate the rate of this process being the formation of Q-balls. Because today you would say something like, oh, the formation of these is non-trivial and is the subject of future work, or some crap like that, you know? We should go back to this language. I love it. It doesn't have to be a scalar field. It could be a fermionic field, just like how the quarks were. In which case they form Fermi balls. There's actually all different kinds of ways you can put quarks together. You can have a dark version of nucleosynthesis where just quarks kind of build up into larger and larger nuclei of these quarks, or fermions rather. You can have it in a phase transition, exactly like the quark nuggets, where some dark phase transition pushes them together. Or you could have Yukawa attractive forces between these quarks, which in the very early universe causes them to form up into very small structures. And these would be a perfectly good dark matter theory. And in fact, there are clickbait videos on YouTube about Fermi balls. So it is definitely real science. That is the category of real science. So I don't really have time for it. I've done some work on forming Fermi balls. It's not that interesting. Essentially what you do is, you have some fermions. They're attracted together by Yukawa force. The scalar radiation allows them to cool. You get Fermi balls. Excellent. They even did simulations showing that it works in real life. You have all this crazy structure formation before radiation domination ends. And then you form these little balls which kind of screen the effect of the scalar force afterwards. So they're just essentially cold dark matter. The final answer of this stuff is that they can actually also form black holes. So just like neutron stars, which have a maximum mass, white dwarfs have a maximum mass, Fermi balls have a maximum mass before which they become a primordial black hole. And depending on what the size of your scalar field and your fermion field is, you can produce a bunch of primordial black holes or a bunch of Fermi balls. And that's the end of the talk. The summary is really macroscopic dark matter is cool. You can come up with some convoluted reason why you should study this, but ultimately it's because, well, we studied the easy stuff already, and this stuff's fun to study. Primordial black holes, hopefully I convince you that they're a little bit legitimate. And big composite states, there's a lot of work to do, fun parameter space to test. Keep working on solar system stuff is my plan. And of course, come chat with me anytime. Oh, I'm going to Australia next week, but eventually I'll be back and then you can come chat with me. Thank you.
Most bagel. Except for the two ball and three ball, you like to remind me which mass should I expect for this ones and the cross-section, section.
So the mass and the size are pretty variable. Like you have a lot of knobs you can turn to make Fermi balls of. So for the particular one we were looking at, you produce Fermi balls from masses that are like completely like very tiny, like small nuggets, to like humongous things, just depending on the actual initial field configuration. Some of this parameter space maybe works less well, but that's the general idea, is you can kind of have them of any size. In terms of the density, for Fermi balls, at least, I would expect them to be more like nuclear density, like a neutron star, but it's not necessarily the case. So it just depends on your theory. And Q balls, similarly, you can play with the knobs.
For the first order QCD patient stuff, did I hear you say you needed 3 quarks?
Yes, so above the QCD phase transition, you should have free quarks, and below it, they hadronize into pions and whatever,
Okay, and so this new phase is the one that has the free quarks.
No, the old phase, when you're much hotter, you have free quarks, and then you have hadronization once you drop below the QCD temperature. And so that's why it's hard for the free quarks to get across and become a pion or something, because they're just so much smaller.
Regarding your asteroid mass black hole moment. So can you go back to your
What was my statement? What was it?
asteroid mass primordial black hole with constraint. So
Like this stuff here.
yes, so this plot is for a monochromatic mass distribution, right?
That's right.
Suppose you have
That's
a
right.
large enough, broad enough mass distribution, then you can push those constraints from left and right, and you can just forward the.
Sure. So if your mass distribution,
The point is, if you modify the asteroid mass black hole can form 100% of dark matter. It's only true if the mass distribution is exactly directed.
that's true. If you have like so a regular-ish log normal distribution, which is actually what you expect from inflationary production mechanisms, it's not so much wider than the monochromatic one that these bounds look very different. It's when you go to a really wide distribution that it becomes this sort of fuzzy ball that I showed here. So, it becomes easier to open up these spaces, but,